Let me start recording. Okay, so welcome everybody to the, I believe to be the 44th edition of the Computability Seminar. So today is my great pleasure to welcome Jeff Hirst, who is going to talk about some thoughts on Hindman theorem. So let me just remind you, for those who are not speaking, please stay muted unless you want to speak, in which case you want, well, to unmute yourself. And yeah, please start.
So I want to thank the organizers for inviting me to do this. I was inspired to give this talk partly by Ludovic's recent talk, where he was describing his ideas about some work that might be done, and that's also the nature of this talk. Though my focus is much more narrow than his, but I'm not announcing new results. If that's what you were waiting for, then I'm sorry. But I did want to talk about Hyman's theorem. This is something that I've been very interested in working on for a long time, and for those people that haven't been thinking about this so recently, I'd like to remind you of what Hyman's theorem is. And basically, it's a statement of combinatorics that says if we have some sort of a finite coloring, I usually think of these things as colorings. You can also view them as maps from the natural numbers into a finite number. So we have some finite coloring of n, then there's an infinite set whose finite sums are all monochromatic. So down here, I've written my monochromatic set, and we're actually saying that we have some particular color here so that everything in H will have the same color. And then whenever you take a finite collection of elements from H, those will also have the same color, right? So all the single elements are the same color, all the sums are that same color, all the sums of three elements are exactly the same color, and so on. So it's always something that I find absolutely remarkable, just as a combinatorial statement, that this actually works. So it is possible also to iterate the theorem, and if you have a whole sequence, a countable sequence of finite colorings, then you can find a single homogeneous set such that when you look at the whole set, it's going to be homogeneous or monochromatic. All the finite sums will be monochromatic for F0. If you just look at the elements from H1 on, those will all be monochromatic for the F1. From H2 on, it'll be all monochromatic sums for F2 and so on. So this is also a very interesting extension of Hindman's theorem. So there's this old paper that I got to work on with Andreas Bloss and Steve Simpson, and we gave some bounds on the strength of Hindman's theorem and the iterated Hindman's theorem. We were able to prove the iterated Hindman's theorem in ACA naught plus. So ACA naught plus looks like arithmetical comprehension, and then one extra axiom that says if you've got a set, then you also have the omega jump of this set. So it's one step beyond arithmetical comprehension, but it's not, as far beyond arithmetical comprehension as many of the other subsystems, right? So it's not like ATR naught or, Pi11 CA naught or something like that. And then over RCA naught, we were also able to prove that Hyman's theorem implies ACA naught. So we trapped Hindman's theorem and the iterated Hindman's theorem both in between ACA naught and ACA naught plus. And so that paper came out in, I think, '84, and we really haven't changed on those bounds on the strength of Hindman's theorem, and it's not from a lack of thinking about it. I did want to mention at this point some related work in a couple of different directions. Of course, well, I will be talking about my notions of how it may be possible to prove the iterated Hindman's theorem in ACA naught, right? And this is something that I've been looking for this proof for quite some time. Henry Tausner has done some really interesting work on looking at computable colorings with really complicated monochromatic sets. So the idea there was to push it up in the other direction and show that Hindman's theorem was not sort of arithmetically true, and try to show that it was stronger than ACA naught. Then I also wanted to mention this work by Montalban and Shore, right, that gives a bunch of conservation results over the iterated Hindman's theorem. I think that this just gives emphasis for, it gives new importance to the problem now, because if we had a better understanding of how strong the iterated Hindman's theorem was, then we would have, you know, more information that we could extract from these wonderful conservation results, right? So that for me just emphasizes the importance of trying to figure out where iterated Hindman's theorem is. So in order to attack this in ACA naught, the approach that I'm interested in using deals with countable Boolean algebras and ultrafilters on countable Boolean algebras. And if you have a finite partition, so a finite coloring of the natural numbers, you can build one of these things that I usually call them shift algebras. And the idea is that it would contain all of the monochromatic sets from your coloring. You can also throw in the finite sets. And then you want it to be closed under unions, intersections, and complements like any normal Boolean algebra, right? And then it's got this one other feature. Since we're looking at subsets of the natural numbers, it makes sense to take a subset of the natural numbers and then subtract a fixed natural number, like maybe 3 from everything. So you go through your whole set, element by element, subtract 3 from each element, and you can create these shift sets. And you can close your algebra up under the operation of shift also. So if you're working in ACA naught, from a finite partition, you can actually give a nice presentation of the shift algebra for a coloring, right? And so what I mean by the nice presentation is you've got a listing of the sets in the shift algebra, where the listing is essentially just a list. You can think of it as a list of characteristic functions for each of the sets in the Boolean algebra, right? And so now all of your sets have sort of natural indices, right? And then you can also include maps from the indices of the various sets to the corresponding indices for unions. So you'd have an operator that took you from the indices for 2 sets to the index for the union of those 2 sets, and so on. So you can do this for, you know, unions, intersections, complements, shifts, all sorts of things like that. So the other thing that you can do in ACA naught at the same time when you're building one of these shift algebras is if there's some other collection of countable collection of sets that you have access to that you want to throw into your algebra, you can do that too. So if we wanted to like throw in all the multiples of 2 as a set into the algebra, we could make sure that that set was included in the algebra. And so you can include other nice sets if you want to. So there's lots of different algebras that you can build. I did want to mention here that this is one of the advantages of working in ACA naught, is that you actually get a nice presentation of these algebras, right? If you try to carry this work out in RCA naught, that's not the case, right? So in this paper 3, I was working in RCA naught, trying to work with some of these shift algebras. And so I had to just like work with sort of enumerated presentations of the algebra. And so the representations of the sets were not unique. It made it messier, but allowed me to prove some results over RCA naught. So there was a justification for doing it. Now I can relax, right? I'm just going to be happy if I can get any result in ACA naught. So I can assume that I don't have such a horrible representation for my algebras. So this is a big improvement. So so we can talk about ultrafilters on these Boolean algebras also, and they're just like the normal ultrafilters that you would see. So you can think of them as sort of large sets defined by the usual characteristics here, right? So the empty set is not a large set. If you have two large sets and you intersect them, it's still large. If you have a set here Y and it's large in the sense of the ultrafilter, then a bigger set will also be large, right? And then to make it an ultrafilter, we need to make sure that either a set or its complement is always in the ultrafilter. So either the set or its complement will be large. So once we have this concept of ultrafilters, of course, the ultrafilter consists of, you know, some collection of subsets in this countable set where we have indices for all of the sets. So we could actually think about the characteristic function for the ultrafilter as some string, infinite string of zeros and ones, some element of Cantor space, right? So if you had 0, 1, 1, maybe that's telling you that the 0th set is not in the ultrafilter and the first set is and the second set is, and so on, right? So you can treat these ultrafilters as being elements of Cantor space. And you can also look at them in terms of the topology on Cantor space then. So if you look at the set of all the ultrafilters, well, the way that you start one of these sequences and it doesn't result in an ultrafilter is if no matter what set you put on next, you're going to wind up with a finite with an empty intersection, right? Then you would want to cut off the paths extending that initial path. And so cutting those off is like creating an open set, right? And then the complement of that will be the paths through the tree, and that corresponds to this closed subset of Cantor space. One of the other things that's kind of nice in thinking in terms of that is if you've got an ultrafilter and you have some set, you know, X in your Boolean algebra, you can say, okay, I'm interested in all the ultrafilters that contain X, right? And those ultrafilters will form an open set. I guess we could argue whether, you know, depending on what your favorite basis is for Cantor set, we could argue whether or not it's a basic open set, but it's certainly an open set within the closed set of ultrafilters, right? It's technically a Clopin set, right? So we have this nice topology on top of the ultrafilters now. And there are ultrafilters that I'm particularly interested in, and I've trimmed my terminology a little bit for these. So we'll say that an ultrafilter on a shift algebra is almost downward translation invariant. So I'm just going to call them invariant from now on because it's a lot fewer syllables. So an ultrafilter is invariant means that for every set in the ultrafilter, you can find a natural number inside the set such that the shift is also in the ultrafilter, right? So this has to work for every element of the ultrafilter, right? And this particular shift amount also has to be an element of the set. Both components of the definition are important here. One of the things that's interesting about this is if you're looking at a shift algebra and you make sure and you throw on all the finite sets into your Boolean algebra there, right? Then if you have an invariant ultrafilter, right? If X is in the ultrafilter, then if you throw away the like a finite initial segment of the set X, right? You're still going to be able to find that should be in the ultrafilter, and you're still going to be able to find one of these shifting elements. So in this situation, there's really not just one of these shifts for every X. There's actually infinitely many shifts such that the shifted set is in the ultrafilter. We'll see something in a few minutes that's actually a little bit connected with that.
Question?
Yeah.
In that definition you just gave, does the n have to belong to x?
Yes. Yeah, so in here, yeah, I dropped out the n in x when I adjusted the definition down here. So n should be an x down here also. Thanks, Carl. So the other thing that I was going to mention here is you may have seen other definitions that look more along this line, where say the set of all the shifts that result in x minus n still being in the ultrafilter is itself large, right? And there's a problem in trying to do that in exactly this sort of second order arithmetic setting that I'm working in here, in that these arbitrary sets are not necessarily in my Boolean algebra. So it has to do with the fact that we've restricted interest to a smaller Boolean algebra, right? If you're working with the full power set of n, then you could use an alternative definition for these ultrafilters. The ultrafilters would turn out to be the same thing as the ultrafilters that are idempotent for Galvin-Glaser addition. Again, when you're working with a countable Boolean algebra, extending the definition of Galvin-Glaser addition is challenging because some of the sets that you need just aren't in the Boolean algebra. So, so this is related to the things that you would see just in the combinatorics literature about Hyman's theorem and its relationship to ultrafilters, right? But it looks a little bit different because we're restricting to this countable Boolean algebra. Okay. So I've wandered off here and started talking about these invariant ultrafilters and everything, and I haven't really said anything about the connection between these and the monochromatic sets for Hyman's theorem. So I did want to say something about that. I've tried to draw a picture down here, which may or may not be helpful. So if we start with the shift algebra that we constructed from some sort of a coloring, it turns out that we can extract a monochromatic set in the sense of Hyman's theorem from absolutely any invariant ultrafilter that we could get. So finding an invariant ultrafilter actually gives us a monochromatic set. So the way that you would construct this monochromatic set is actually reasonably straightforward. So you start with a monochromatic subset in the ultrafilter. So I try to draw a number line here, and then I'm supposing that I've marked some natural numbers that are all the same color. So all of these little marks are places where, say, the coloring made those numbers blue, okay? And then what I'm gonna do is look for a potential shift here. So if you look at this gap, this first gap, right, that seems to recur pretty frequently later on in my set, right? So I'm thinking that I could take my monochromatic set here and shift by this gap and have an interesting outcome, right? So I made a fresh copy of my integers here, right, with the ones marked that are all the same color. And now I'm going to shift those to the left by this distance, right? And so when I shift them, I'm getting a collection of new natural numbers here, of course, and we'll just throw this negative stuff away. So let me throw the negative stuff away and mark the amount that I shifted by, right? And now I have two subsets, both of which are in my Boolean algebra. So I can intersect them, right? And I'll get another set in the Boolean algebra. More to the point, I was picking X so that when I did the shift, I would still get something in my ultrafilter in my invariant ultrafilter. So this intersection is actually also in the ultrafilter. So now at this point, I can start looking at some of these shifts and see, you know, if there's one, well, there ought to be an amount for a shift where I could pull the same trick again and get these circled elements after shifting to still all be in the ultrafilter. So this first one doesn't seem to work because it's too short. So if I look at this gap here, right, then up here, that gap's not working at all. And here, that gap's not working at all. But I think if I go this far out, then at least one time it repeats, and we'll assume that it actually repeats on some large set in the ultrafilter. So when I do that shift, right, so I'm picking out my second shift element here, and then I could shift the elements down and look at the intersection, right? And what you can see here is when we're picking these elements out from the intersection, right? If I look at this element, it has the right color, right? If I add on the first element to that, I'm still in the right color. If I add on the second element, then I'm still in the correct color. If I add on both the first and the second element, then I'm still in the right color. So you just iterate this process and you can eventually build the monochromatic set. And I don't know. I'm not sure that the picture actually helps any more than just looking at the proof where it talks about the sets and builds the intersection sets, but that was worth a try. So yeah, finding these invariant ultrafilters is certainly connected somehow to monochromatic sets. And it turns out that if you can find an invariant ultrafilter, then you can find a monochromatic set for the iterated Hindman's theorem, right? And vice versa. So this is an equivalence that's actually provable over RCA naught if you're willing to put up with the, you know, annoying presentations of the shift algebra that you see in that paper. Okay, but this explains why I'm obsessed with these particular ultrafilters, right? I mean, I'm interested in finding monochromatic sets for the iterated Hindman's theorem, right? So if I can find the invariant ultrafilters in ACA naught, then I've solved the problem. So that's my goal. So we've talked about shifting sets, right? But you can also shift ultrafilters, right? So it turns out that the way this works is shifts and set operations just interact in a remarkably predictable fashion. So if I have a pair of sets X and Y, and I want to intersect their shifts, I can either shift them both and intersect, or intersect them and then shift them. So if you think of these as sort of physical processes, it's not so mysterious, but it's certainly awfully convenient. And the same thing works with complementation also, right? So if you want to find the complement of the shift of a set, you could just take the complement of the set and then shift, and you'll get exactly the same thing. So if we've got an ultrafilter, we can define the result of adding 1 to the ultrafilter by saying that a set's in the ultrafilter plus 1 if and only if the left shift on the set is in the ultrafilter. You might say it seems strange to use addition here, but actually it works very nice with this other notation. You can essentially like subtract 1 from both sides of the epsilon statement there. So it gives you a neat sort of algebraic shortcut here. So this shifting, if we're shifting all the sets in the ultrafilter, it turns out that the result is an ultrafilter again, and that's not too surprising in terms of this interrelationship between shifts and intersection and complement, because they interact so well. It actually preserves the ultrafilter if you just shift every set the same amount, right? And then another thing that's worth noticing here is if you have U and V and they agree on a lot of sets, right? So our sets are lined up in order, right? Because we have this nice countable Boolean algebra. So if U and V, if they agree on the first k sets, right? Then if I look at U plus one and V plus one, well, they agree on some k sets, right? Maybe not on the first k, but they agree on a bunch of sets, right? And you can extend this and actually show that this function where you're adding one to the ultrafilter, where you're shifting the ultrafilter, is a continuous function on Cantor space, right? On the space of the ultrafilters. So once we have, the set of ultrafilters is a nice closed set, and now we have a continuous function on a closed set. So you can start doing topological dynamics on the space that has the ultrafilters in it. So here's another theorem from that very old paper from the 80s, right? So if you have a compact metric space, which our ultrafilters form one, right, and you have any sort of a continuous function, then for any element, you can find another ultrafilter in the orbit closure of that element, such that everything in the orbit closure of that element is uniformly recurrent, right? What I'm going to be mostly interested in here is saying, oh, I can find some U such that everything in the orbit closure is uniformly recurrent. So let's try to unwind the terminology a little bit, at least in terms of our setting here. So if I want to think about my continuous function as just being that +1 function, then this says that you can find this ultrafilter U such that everything that's in the closure of, so I wrote down the forward orbit here, right? So you have U and U plus one and U plus one and so on. Right, you take the closure of that set and everything in there will be uniformly recurrent, right? So that's great if you remember what uniformly recurrent means, so I probably shouldn't tell this story. I was talking to my wife about this stuff one day, and I said, so let me remind you that an element is uniformly recurrent if, and then before I could finish the definition, she said, well, I know what a uniformly recurrent element is. So just get to the punchline. So anyway, I'm going to bore you with my comments about uniformly recurrent. So it just means that for every k, and this is kind of interesting. Usually you see this as stated as every epsilon, but I can take advantage of the fact that we're working in this situation where we have a nice topology on the sets given by our enumeration of the Boolean algebra. So in this setting, it actually means that for every k, there's some m such that whenever anybody throws you an n, within the next m jumps from the nth jump of v, right? So you kind of start with v and hop along n times using your operator here. And then within the next m hops, you're going to get back to something that agrees with v on the first k sets, right? So it's very close to v. So the idea is we're kind of hopping around in this ultrafilter space, but every element in the forward orbit closure of U is revisited very, very regularly, right? So you're looping back to all of these points on a really regular basis. It's a very, very sort of interesting situation. So yeah, here's the underlying question now. So that lemma was provable in ACA naught. So you can look at this forward orbit of this element U that you get, and then you can say, is there an invariant ultrafilter in that orbit closure? And if the answer is always yes, then you know that there's always an invariant ultrafilter. So this would be a way to carry out a proof in ACA naught, provided that you could find the invariant ultrafilter in the orbit closure using only, the set theoretic strength or the comprehension strength that's available in ACA naught. So at least in some circumstances, the answer is absolutely yes, there will be such an invariant ultrafilter, and that you can prove in ACA naught that it exists, right? So if you're in a peculiar sort of situation where the orbit is actually finite, then you can show that there has to be an invariant ultrafilter. And basically just look at the action of that +1 operator on the ultrafilters, and you get this finite loop, right? And then if the first set is not invariant, then there's some shift around that finite loop where you're going to hit an ultrafilter that is invariant. These orbits are not always necessarily finite, though. So it's nice to think about what could happen with regards to the infinite orbits, right? And I have an idea for what to do with the infinite orbits, and that's based on this notion of a witness set, right? So let me tell you what a witness set is. So a witness set is just a set in the ultrafilter, right? And I've listed the elements of the set out here. So it's a set in the Boolean algebra, right? And we'll say that it's a witness set if there is some ultrafilter V such that the witness set is in V, and for every n, the shift by the various set elements is not in V, right? So basically there is a V such that W tells you that V is not invariant, right? So the witnesses witness that some ultrafilter is not invariant. So one of the things that's cool about a witness set is there's an associated nested sequence of Clopin sets. You can start with all the ultrafilters containing W, and then all the ultrafilters containing W intersected with the complement of this shift. So this is saying, this shows that W0 doesn't show that the ultrafilter is invariant, right? And so on. So you can see that these sets are actually decreasing in size, right? We're intersecting more and more things, so they decrease in size. And if you intersect all of them, you actually come up with exactly the non-invariant ultrafilters that are witnessed by that particular witness set, right? So I'll talk about these sequences of open sets associated with witnesses again in a few minutes. So the thing that I had noticed more recently that actually has me kind of excited is thinking about these witnesses sets. And when you look at the definition here, it looks like a sigma 1-1 formula, right? So we're saying that W is a witness set if there is an ultrafilter V. So if there's a set, right, such that W is in V, and for every n, actually for every n in W, well, I guess for every n, the shift set W minus Wn is not in V. So the rest of this is all sort of an arithmetical predicate, right? It's only the first existential statement that there is an ultrafilter that really makes it look like a sigma 1-1 formula. But since we're working in the orbit closure of U, right, the way that any set gets into the orbit closure is being approached pretty closely by something in the forward orbit of U by our +1 operator here, right? So actually we can say that there's if for every n there's a j such that this holds, right? So sort of no matter how far out we go in the sequence, right, we can still find something in the forward orbit of U that contains this set, right? Well, that happens if and only if there is this ultrafilter that is non-invariant and being witnessed by W, right? So this is the existential statement about the ultrafilter V, right? But this version of it is talking about for every n there's a j such that something arithmetical happens. And so what this means is that we can actually replace our definition with a definition which is arithmetical. So the set of witness sets is actually arithmetically definable. And you can do even a little bit better than that. So if you've got your Boolean algebra here, and we've got all of our sets enumerated here, we can talk about something being a minimal witness if it witnesses that some ultrafilter is invariant and none of the previous sets witness that that particular ultrafilter is invariant. So it turns out that the set of minimal witnesses is also arithmetically definable. So we have this really simply defined set of indices of minimal witnesses. So I feel like I'm defining a lot of stuff and then not telling you what it might be good for. So maybe it's time to talk about that. So if we start with minimal witnesses, then it turns out you can build some very interesting sequences of open sets. So let's suppose that we've got the sequence of minimal witnesses, right? Then we could sequentially select open sets. And you can think about, right, we had these open sets that were decreasing neighborhoods, right? Shrinking and shrinking neighborhoods around particular associated with each particular witness set. So we can select open sets that are associated with witnesses that are so small that they omit forward orbit elements, which have minimal witnesses of arbitrarily large index, right? So let's suppose that we can sequentially select open sets that satisfy that, right? If that process never halts, what are we going to wind up with? Well, we can do it in such a way that we'll come up with a sequence of open sets so that no initial segment is a cover of the entire orbit closure, right? But every non-invariant ultrafilter will eventually get put in one of these open sets because we're picking open sets associated with the witnesses, right? So if you can actually get that sequence to that process not to halt, then it turns out that the orbit closure is a closed set. So by the Heine-Borel theorem, right, we had this collection of open sets, which is not a cover of the entire space, right? Because of the Heine-Borel theorem, right? No finite initial segment covers the entire space, and so the entire sequence can't cover the entire space. And so that tells us that some ultrafilter lies outside the union of the open sets, right? And that ultrafilter would be invariant. So this gives us a way to find an invariant ultrafilter, essentially relying on the Heine-Borel theorem, right? Which was kind of a surprise to me, right? Now there is an issue associated with this, and that's that I said here, if this process never halts, right? And it's not clear that you can always keep picking these open sets. So the question is, what happens if the process halts, right? And in particular, I don't even know what happens in the instance where maybe you only have finitely many minimal witnesses. I think in these situations, it may be possible to use the uniform recurrence to show that there's an invariant ultrafilter. Certainly, recurrence helps when the orbit is finite, right? And that's a result that I mentioned before, right? So now I'd like to know if uniform recurrence can help me in the situation where the process that I was just describing turns out to halt at some finite state, right? And then of course, I guess if we were working in a strong enough axiom system, then yeah, we'd know there was always an invariant ultrafilter, right? So the real question is, can we carry out this part of the proof in ACA not? The surprising thing to me is that we can get a handle on those witness sets inside ACA not. So that's what I've been thinking about. That's new. So that's what I wanted to say about this, and here are some references.
Okay, thank you very much for this very nice talk. Is there any question? So I see that Andrea has a question.
I was not planning to ask a question, but let me, as long as I seem to be asking a question anyway. Let's see, iterated Hindman's theorem and plain old Hindman's theorem without the iteration. Is there a significant difference there? Because I usually think in terms of plain non-iterated theorem.
That's a really interesting question, and we still don't know, right? Because as far as we know, they may collapse, they may be the same, they may be different. If we could separate them, that would be wonderful too, right? I mean, I have my process that I've been working on here, but I know I could be working on the wrong side of the question. So maybe trying to separate Hindman's theorem and iterated Hindman's theorem would be a viable approach.
Maybe I should make a comment which might be obvious, but might be worth making anyway. From the point of view of reverse mathematics, the gap, the unknown part, is a little plus sign, ACA 0 versus ACA 0 plus. But if you look at it from the point of view of recursion theory, given the partition in Hindman's theorem, how complicated relative to that will the homogeneous set be? And there, as far as I know, the best results are also still from that prehistoric paper, that you can always get the homogeneous set recursive in the omega Turing jump, but the only lower bound is one Turing jump.
Right.
Go to reverse math, one Turing jump is as good as any finite number and not a lot of the distance. But from 1 to omega looks to me like a pretty big gap.
Yeah, well, I think that's actually related to Henry's approach to this problem, that he was trying to push, construct colorings that would push the complexity of the homogeneous sets up the arithmetical hierarchy, and he thought if we could prove Hindman's theorem in ACA not, then there would be an upper bound on for the complexity of the monochromatic set for every computable coloring, right? So if he could kind of unleash that and just push it up beyond any finite level, then we would know that Hindman's theorem was not provable in ACA not, right? So that was part of his goal, and yeah, he made some progress on that, but then he said, the arguments keep getting.
May I comment on that?
Yes. Yes.
Well, first on Andreas, this is an extremely tiny correction, but I believe if you have a computable instance of Hindman's theorem the upper bound for the solution is not the omega jump, but the omega plus first jump.
Yes.
So much the better for what I was saying. Bigger gap yet. In what
So yeah, and on Henry's work, I don't believe he actually got any stronger result than in the original Bloss-Hirst-Simpson paper, because he showed that there was a computable instance with no sigma 2 solution, but since every infinite sigma 2 set has an infinite delta 2 subset, that actually follows from the result in your original paper. So I think that, and still those are the, as far as I know, those are the best results known. And well, that and the coding result that there's a computable instance such that all the solutions compute zero jump.
Yeah, I guess the bounds. So the improvement that Henry gave in terms of lower bounds and so on was more about saying there is a way of constructing this by building some kind of intermediary object, which are called like half match and full match, and saying, oh, by iterating half match, we obtain a full match, and by iterating omega times a full match, you get a finite solution to Hindman theorem, and trying to show that how hard is it to get this intermediary object, and to kind of give an idea of how hard it is to build the definitive object.
But it's not clear to me that Henry's proof gives any improvement on the upper bound in the original Bloss-Hirst-Simpson paper.
No, it does not. It does not.
Though it is a very nice proof, of course.
So actually, so just to comment, I find interesting that there are two ways in which we, so the question from Andreas about infinitary Hindman versus Hindman, so is it stronger or not? It makes me think about the fact that we don't know any proof of Hindman for when we restrict homogeneity to sums of length at most 2 from the full Hindman theorem. So which means that when we require to have an infinite set of integers so that the sums of length at most 2 are monochromatic, we don't know a proof of that, which is not a proof of full Hindman. But we also don't know if a proof of full Hindman, which is not really a proof of iterated Hindman. So there are two ways in which we don't know separations.
And also the lower bounds in the original Bloss-Hirst-Simpson theorem have been redone for sums of length 2 or length 3, depending on the theorem. So it's amazing how little we know about this.
Yep. Any other question? No. So thanks again, Jeff, for this very nice talk. So as you know, we usually have some informal discussions afterwards. So if you want to stay, we can split into breakout rooms.